Hello. This video is about what is called first isomorphism theorem. And it's a very basic result about a homomorphism, really. So we have a homomorphism between two groups. Then, well, homomorphism or just a map, it will always be possible to decompose, to factorize it into a surjective map onto its image, followed by an injective map, just an embedding of the image inside H. So just to remind you what the image of any map is, well, just a collection of all the values of that map. And that is always a subset in the target. So in our case, that will be also a subgroup. We also have, so yeah, the first isomorphism theorem will be an alternative description of this image, or a kind of further factorization. The factorization will involve the kernel. The homomorphism, it's another subgroup associated with a homomorphism. It is a collection of all elements in the first group, in the source, which are mapped to the identity. So this is also a subgroup. With any subgroup, we can form a set of cosets. So that's what I'm going to put here. The set of cosets with respect to the kernel. There is always a canonical surjection, just computing the coset of an element. So the first isomorphism theorem says that there is a canonical also isomorphism between the two. Very natural isomorphism between the image and the set of cosets by the kernel. Well, just to remind you, okay, what are cosets? So this is the set. Well, we have to choose a side of the right cosets with respect to this subgroup. So they are subsets of the group G, which consist of all possible products of a given element, so we fix G, and then we look at all possible elements in the subgroup, in our case the kernel, and form the product. So that is what a coset of G is, what the coset of G is. So this isomorphism will be identifying them with something else. So what they will be identifying them with is just the element in here, the image of G. So let me call it H for convenience. And then this identification will be exhibited by the following characterization of this coset. This is nothing but everything which is mapped into H. So that is called the pre-image of little h in the target, and this is all group elements which are mapped into H, including our chosen G. So these two, I'm going to argue, are the same. That is the key for the whole first isomorphism theorem. So that is going to be proved by just one single line computation. Not a very difficult to prove result, but quite convenient. Okay, so what am I having here? All elements which are mapped into H. So one is G, the other is F. Let's have this written. And then what I have to show is that they themselves, this F and G, they are in the same coset, so they differ by something which is in the kernel. Well, okay, let's do the computation. So from here, what we can write is just rewrite this equation. It's an equation in the group H, and we can rewrite it using inverses. So instead of this equation, we can equivalently write it as, say, phi of g inverted multiplied with phi of f is equal to the identity. So basically take this and multiply with its inverse both sides of the equation. But phi being a homomorphism allows us to rewrite this a little bit further. First, the inverse can be put inside, but then just the homomorphism property allows us to write it like that. So now we have a single element in G, sort of the difference of G and F, which now is mapped to the identity. So these two conditions are equivalent. F and G having the same images, having the same values, and the difference of them being identity. So that's really just group cancellation action plus homomorphism property, nothing else. Very basic, very kind of shallow proof. So on this side we have F and G being in the same preimage. On this side we have G inverse F being in the kernel. Or we could rewrite it as F being in the coset of G. So just what we want. So F is in here, if and only if F is in here. So they are, these subsets are the same. And this is the isomorphism here. So we assign to a coset, well, just that H. Really we assign to a coset any value of phi on that coset, and all the values are the same. So in particular, phi is constant on cosets of the kernel. So it's just the same value for any element in here phi takes. That's what it means. And that really defines the map, and that map is 1-to-1 just because of this. So we have this isomorphism. Yeah, let's put it to immediate use. So corollary as follows. Again, let's assume that we have two groups connected by a homomorphism, and assume that, yeah, they're both finite, and the index in the source of the kernel, which is equal to the ratio of the orders, is also equal to the order of the target. So let's assume all that. Then we have a conclusion that phi is surjective. It's onto. Why? Well, simply because of this isomorphism. The image, the order of the image by this isomorphism theorem is nothing but the order of this set. So the index, the number of cosets, the index of the kernel. And if it happens to be the same size as the H, then these two are the same. The image by its very nature is a subset, but now it becomes everything in H. So we're done. One important remark, maybe just putting it in this corner. This is a group, and so because these are isomorphic sets, this is also a group. And the group structure here is just the group multiplication on the image. So when we multiply values of phi, it's as if we're multiplying cosets, or alternatively pre-images. So we have this group structure on the set of cosets, the quotient set, and the group structure in terms of this pre-image characterization, so it's just like that. This looks like an equation of elements, but it is not. This is a subset. So both subsets in H. They are subsets in G. There are elements in G which go to the fixed value. So here there are all elements in G which are mapped to value H. Here there are all elements in G which are mapped to value H prime. Not surprisingly, their product will be always mapped to H times H prime. So we have this obvious operation of multiplication on subsets which are preimages, but now we describe them as cosets, and so we have this operation on cosets which gives rise to the construction called quotient group. So that will be discussed in another video.